I'm Dave Abitangelo here with Group 3 of the Hydraulics Project.
I am Jacob Sander, and we're out here on the coldest day of the year filming.
And I'm Jacob Dawson. I'm a junior here, and here's what we're going to talk about. Good evening, folks. As we mentioned, this is Group 3 with Jacob Sander, David Abitangelo, and myself, Jacob Dawson. And today we're going to talk about water hammer and siphon. We're going to talk about what exactly is siphon. Also, what the applications are: commercial, residential, and industrial. We're also going to show you an example problem using Bernoulli's equation and work through it. With water hammer, we're going to talk about what exactly that is, the applications in which we run into this issue, and also how to fix the issue. We're going to show you the water hammer equation also. As you see here, we have a container filled with a fluid, in this case water. Container A has to be at a higher elevation than C for this application to work. The reason this works is because the medium potential energy at point A begins to move up the tube once the suction is applied to point C. Once the water begins to flow and reaches point B, the low pressure area, it gains high potential energy, causing the water to flow down the tube to point C. Once the siphon starts, it will remain to flow unless air enters the stream, breaking up the surface tension and hydrogen bonds. If you raise the cups to the same level, the water will also quit flowing once it finds equilibrium, as seen here. Siphons can be used to dewater holes on a job site when a pump is not present. It can also be used around the household, transferring one fluid from one tank to another tank without a pump or a hand pump.
So here we have the Bernoulli's equation, and we are going to learn how to work out a problem here with our siphon. So here we start out, we have our pressure energy, and then you have potential energy. And the reason it's potential is because you have your height, and our height is right here from the top of this water level to the bottom of our point B. And then you have kinetic energy, which this is kinetic because you have your velocity. Our velocity is going to be how fast the water is traveling down the tube. So to start out our equation here, our pressure is going to be the same in both. So we can go ahead and cross out our pressures. Now our density is water, so the density is going to be the same throughout the equation. So we can cross out the density. Now we'll rewrite this here, and we have our gravity times your height of A plus half of your first velocity squared, which equals your gravity times your height of B plus half of your velocity, the second velocity there. So we're going to go ahead and look throughout our variables here. And we can go through, we have our gravity and our height at point A, which will be 1.15 meters. And now we're going to move over here, and we have half times our first velocity. Now our first velocity at A, as you can see, our water is just sitting in the cup. So therefore, we can assume that the velocity would be 0 here at this point. So if you plug 0 in here, you can just cross that out. So you come over to this side of the equation, you have your gravity, and then you have your height at point B, which B is at the very bottom. It's at the datum point. So we assume that B is 0. Therefore, you can cross that one out. Now if we rewrite this, we have our gravity times your height at point A equal to the half of your second velocity squared. Now, in this equation, we are trying to find the velocity at point B. So we're going to go ahead and solve for this. So from this point, now we'll rewrite it so that we can solve for V2. So now we're at this part of our equation. It's real simple. We'll just go ahead and plug in our numbers for these. So we're going to have V2 equals radical 2 times gravity, which is 9.81 meters per second. And then we're going to have our first height, which is 1.15 meters. And that will give us our final velocity of 4.75 meters per second.
Okay, let's talk about water hammer. Water hammer is a sudden shutoff of water flow. Shutoff has to be considered with the equation of T equals 2L divided by A. T is the minimum time a valve can close. L is the length of the run without change, like a T, an elbow, or another valve. A is the cross-sectional area of the pipe. As you can see here, the water is shut off with a swing check valve, causing a reverse flow of water and pressure shock in the lines. Water hammer can create great force, damaging equipment, destroying product, and potential harm to employees in the workforce. Water hammer is when the force of water is accelerated across the path, slamming into elbows, T's, and valves, resulting in vibrations, damaging fittings, and equipment. Water hammer arresters can prevent the issue of water hammer if correctly placed. When the acceleration of the water is stopped quickly by the valve, the returning force of the water will expand into the arresters and dampen the shock. Water hammer has many variables when it comes to solving for it. These include C is equal to celerity or wave speed. That's L divided by T. D is equal to inside diameter of the pipe. E is equal to composite elastic modulus. E sub F is equal to elastic modulus of the fluid. E sub P is equal to the elastic modulus of the pipe material. L is equal to the pipe length. T sub W is equal to the wave travel time. W is equal to the pipe wall thickness. Delta P is equal to maximum pipe pressure increase in water hammer event due to sudden valve closure. Delta V is equal to change in velocity in water hammer. And the last one is your fluid density. Okay, here's what you need to take away from our video. Water hammer is an occurrence when water is flowing through a pipe and the valve is abruptly closed. Water hammer can also occur in sudden changes directions like T-sections and 90s. Water hammer can be reduced when arresters are used. The reason for this is because when a surge of water slams into the pipe, it has nowhere to go. Once the surge comes, the water from the surge recoils into the arrestor so that there is a buffer for the water not to slam into the pipe. Water hammer can also be corrected when a valve is closed slowly. This is because the water pressure changes much slower, so there is no great surge when it hits the valve. Siphon. Energy is the same at all points in the siphon tube. It changes between potential energy, pressure energy, and kinetic energy. Energy type and magnitude in the siphon tube with consistent velocity. Inlet of the siphon tube is potential energy is medium, and pressure energy is medium. High point of the siphon tube. Potential energy is high, and pressure energy is low. Outlet of the siphon tube. Potential energy is low,